the screen that I'm sharing? Okay, good, great. Cool. All right, so where did we stop earlier? Oh, we were talking about heat and temperature. Yeah, we were saying that temperature is a measure of how hot or cold an object is, and we can usually distinguish that by our sense of touch, by feeling the objects. And the base units or SI unit for temperature is the Kelvin. So given the temperature in Celsius, we need to convert often between Celsius to Kelvin, and that's simply by adding 273.15. The 0.15 just gives extra precision and accuracy, but usually we'll just use 273 just for simplicity. Degrees Celsius plus 273, for example, unless we were specifically given to use the 0.15 as well. Okay, so let's look at some examples of how we convert the temperature from Celsius to Kelvin. So here are some temperatures. Water freezes at 0 degrees Celsius. So our conversion Kelvin is equal to the temperature in Celsius plus 273. So for these examples, we'll just use 273 as the conversion factor instead of 273.15, just for simplicity. So try to convert these temperatures. 0 degrees Celsius for the freezing point of wet water. And then for the second example, we have here the temperature of liquid nitrogen at atmospheric pressure, 63 kelvins. So you need to convert 63 kelvins to degrees Celsius. For question number 3, we have two temperatures given in Celsius, 46 degrees Celsius and 60 degrees Celsius. How do we convert, or what is the equivalent temperature in Kelvin? And then finally, we want to convert the temperature difference. So 14 degrees Celsius is the temperature difference, or the change in temperature between two different temperatures. Okay, so try that for a bit, and then we'll see how we do the conversion of these temperatures. All right, let's do the first one, 0 degrees Celsius. So if you're going from Celsius to Kelvin, it's rather straightforward. You just add that 273 or 273.15. So I've mentioned we'll use 273. So that means 0 Celsius plus 273, that's just 273 Kelvin. All right, straight and simple like that. For the second case, you're converting 63 Kelvin to Celsius. So that means you sort of have to isolate Celsius here. So to get the Celsius temperature, you have to get the given Kelvin temperature and subtract that with 273. All right, because for you to isolate degrees Celsius from this conversion equation, you have to remove 273, and 273 is tied to degrees Celsius via this addition sign. So you have to do the reverse of addition, which is subtraction. So you subtract the right-hand side and the left-hand side, subtract it by 273. And so the Celsius temperature will be Kelvin minus 273. So the Kelvin temperature is 63 minus 273. You should have a negative 210 degrees Celsius for the temperature. 63 Kelvin should be equal to negative 210 degrees Celsius. Right? So we can see here, converting from Celsius to Kelvin, you add 273, and converting from Kelvin to Celsius, you subtract 273. So you have those two equations for converting between Kelvin to Celsius and Celsius to Kelvin. Okay, so for the third question, it's rather straightforward now. Then it's also just Celsius to Kelvin. So we will add 273 to each of those. So 46 degrees Celsius plus 273 will give you 319 Kelvin. And similarly, 60 degrees Celsius plus 273 will give you 333 Kelvin. Okay, so relatively straightforward conversions there from Celsius to Kelvin. Okay. Now for the temperature difference, when you're getting the temperature difference, okay, you either get the temperature difference, so 14 degrees Celsius. This is actually the temperature difference between the two temperatures given in question 3. So in question 3, notice you have 60 minus 46 is 14 degrees Celsius. So this 14 degrees Celsius actually came from 60 degrees Celsius minus 46 degrees Celsius from question number 3. Okay. Notice that if you subtract the temperatures in Kelvin, okay, so from the conversion, you do, so note that if you do 333 Kelvin minus 319 Kelvin, meaning if you subtract the converted temperatures that are in Kelvin, 333 minus 319, you will find that that's equal to 14 Kelvin as well. Right? So you can see here that if you're getting the temperature difference, if you compare the two temperature differences that were converted, these two, you will see that 14 degrees Celsius is equal to 14 Kelvin, right? It's quite surprising, isn't it? So if you're getting temperature difference, degrees Celsius will be equal to degrees Kelvin. And the reason for that is temperature difference is, of course, say delta T, or temperature difference, is subtracting two temperatures. So for example, if you subtract 60 degrees Celsius plus 273, the converted this one, the converted form of degrees Celsius to Kelvin, okay, and subtract that with the whole 46 degrees plus 273, subtract this whole thing, 46 degrees Celsius plus 273. You have there a minus 46, so you have a minus in front of a bracket, and we learned last time if you have something multiplied outside a bracket, this is multiplied to each term in the bracket. So the minus sign is multiplied to each term in the bracket. So you have minus 46 degrees Celsius and you have minus 273. So you'll notice that you have plus 273 and then you have a minus 273. So effectively, when you are taking the temperature difference, the conversion factor 273 cancels each other out. Yeah, so this 273 cancels each other out, and therefore you are only just subtracting the actual temperatures, 60 minus 46, which is 14. 14 degrees Celsius, and that's also 14 Kelvin because you did the conversion by adding this 273. Does that make sense? Yeah. Okay, so it's only when you're getting the temperature difference where you can just directly subtract the two temperatures without doing any conversions. And you can just simply change the unit from Celsius to Kelvin if it's a temperature difference, right? Okay, cool. Right, so yeah, so temperature, it's how hot or how cold an object feels to the touch. And we've seen that the SI unit is the Kelvin, and we've learned how to convert temperature from Celsius to Kelvin and Kelvin to Celsius. And we've learned how to get the temperature difference and analyze the unit for the temperature difference. Now, if we look closely into the material, like look at what's happening microscopically inside the material when its temperature changes, and we look at the atoms and the molecules in the material, as we can see in the figure here in the lower right side of the slide. So these are individual atoms and, let's say, molecules in the material. The temperature of the object will actually affect how the atoms behave. So the temperature will cause the atoms to move. We will see in the next lecture that temperature is a manifestation of a form of energy called heat. Okay, and if you have this heat or thermal energy, then this energy will cause the atoms in the material to vibrate. Okay, and the vibration of the atom will cause it to, of course, move to and fro, and will cause it to collide to the neighboring atom. And the collision of one atom to its neighbor will cause it to impart some of its energy, some of its thermal energy to the neighboring atom. And so if we look at the microscopic behavior of the material, we will see that the temperature of the material will change because of the vibration of the atoms. So here is an example of a material, a strip, a rectangular strip, and we see here the atoms. If you put the material close to a source of heat, like a flame, notice how the atoms near the flame vibrate faster compared to the atoms farther away. Right? And as the atoms closer to the flame vibrate, they collide to the neighboring atoms, and therefore they impart some of their energy. The temperature of the neighboring atom will then increase, making it to vibrate as well and collide to the next atom, transferring some energy. And that goes on until the energy is being transferred to the last atoms at the farthest end of the material. Okay, and when that happens, you'll see here in the beginning, the temperature of the material is not uniform. So closer to the flame, you have a higher temperature, faster moving atoms, and represented by the red dots. Okay, but as energy is being transferred to the atoms at the end, notice how the temperature of the material becomes more uniform. The atoms vibrate with similar speed, and you see here they're all red, meaning they all have the same temperature. So if you look at the microscopic picture of temperature, it tells us about the vibrations of the atoms that make up the material that is becoming hot. Right, and it's because of this vibration of the materials, of the atoms in the material, that sort of explains the behavior of materials when their temperature increases. So typically, when the temperature of a material increases, the atoms and molecules vibrate faster. And because of their vibration, their movement, they tend to move farther apart. So that's the reason why most substances expand when they are heated, and those substances contract when they are cooled. So if you can imagine the atoms vibrating as they become hotter, their vibration becomes more intense, and so the atoms move farther and farther apart, and that causes the material to expand. And the expansion can be quite dramatic, that we can observe that with our eyes, and we can observe macroscopically what is happening in the microscopic level. So yeah, so for example, you've probably heard that if it's hard to open a jar, then it will be useful to run the lid under hot water. Okay? And what happens is that the lid, which is like more conductive than the glass, will expand faster compared to the glass. And so you have the expansion of the lid, which causes it to loosen a bit, and it will help you open the jar easier. If you noticed when you're driving on the road, you'll probably notice gaps between the roads. Even if it's a paved road, you'll notice like gaps, or those fine lines between sort of blocks of concrete, and those gaps are intentionally placed to accommodate the expansion of the concrete or the road during hot weather. So the next time you drive on the road and you feel the gaps with like your car, when your car passes over them, remember that those gaps are to accommodate the expansion of the road when the road heats up. And it's quite dramatic. I remember maybe 2 or 3 years ago, hearing a news about a new bridge that was built in Whangarei. So it was supposed to be a drawbridge, that the bridge which can open to allow boats to pass through. And I think they failed to, they made a mistake in calculating the expansion of the bridge. So during one hot summer, the bridge actually expanded so that it was not able to open because it locked together. So thermal expansion can be quite dramatic. You can also see here railroad tracks that have not accommodated the thermal expansion of the railroad track during hot temperatures. Because there's no space for the railroad track to expand, it actually warped in this manner. So thermal expansion is really quite dramatic. So there's a question there, don't glass bottles with water explode in the freezer because the ice expands in comparison with liquid water, or is it a different mechanism? That's a very good point, Oksana. And we'll see at the later part of this lecture that although most substances expand when they are heated and they contract when they're cooled, water has a peculiar behavior. So it's quite different for water in that you're right, when it freezes, the water sort of expands. And we'll see why at the end of the slide, but that's a very good point. And indeed, the expansion of ice when it freezes can also be quite dramatic, that it can cause the glass bottle to break. Yeah. Yeah, but in general, most substances expand when the temperature increases, and most substances contract when the temperature decreases. Water is just an exception to that. Okay, thermal expansion is also the concept, the mechanism behind how a thermometer works. So the thermometer measures the temperature of the system via the expansion of a substance. So the mercury in glass thermometer, or the alcohol in glass thermometer, as we can see here, measures temperature via the expansion of the liquid inside the thermometer. So the liquid inside the thermometer expands faster than the glass, so that if the temperature increases, then the liquid inside expands. So say if the temperature increases, the liquid expands, for example, and goes up to that point. Liquid expansion. And the thermometer is calibrated so that the expansion is proportional to the rise in temperature, to the change in temperature. Okay, and then we'll just read the temperature off of the scale in the temperature in the thermometer. Similarly, in the thermometers, the thermostats in the ovens, they're composed of a coil of metal, two metals that have different expansion rates. And so when the oven becomes hot, this metal expands, and so it elongates, and there's an arrow at the end there that then moves, and we just read off the temperature from a scale. Yeah, but the movement of this arrow is because of the expansion of a metal coil inside as a result of the increasing temperature. Yeah, decreasing the temperature will of course cause the metal to contract, and so contracting the metal will move the arrow in the anti-clockwise direction, giving a lower temperature reading. Yeah. Okay, so thermal expansion is quite an important concept. Okay, I had a student last year who works in the Air Force, and they said that one day they were planning to fly over the Pacific. So very early in the morning, they filled the gasoline tanks of their aircrafts to the full, like to the brim. So they really filled it to the brim, but there was some delay, and it reached them around noontime. They were still in the tarmac, and the temperature of the tarmac really rose very, very high. The gasoline inside their tanks expanded so much to the point that it overflowed out of their aircrafts, and they had to, the fire truck had to come and clean up the gasoline that poured out onto the tarmac. So thermal expansion can really be dramatic, and yeah. And it can, it can be observed by the naked eye. All right, so relating then, let's have a mathematical expression for thermal expansion then. So we've seen that when the temperature increases, the length or the volume of the material will increase. So if we assume that an object has an initial length L0, Okay. So that's an object with an initial length L0 at an initial temperature T0. Okay, when the temperature increases, say by a factor of delta T, that's the change in temperature delta T, then the object will expand and the length will therefore change. Let's quantify the change in length as delta L. So delta L is the change in length there. The change in length will then be proportional to the change in temperature, right? So the higher the temperature change is, the more expansion you will have. And so, yeah, you have this direct proportionality for the expansion and the change in temperature. We have here a constant alpha. So this constant here is the Greek symbol alpha, which is called the coefficient of linear expansion, which tells you it's a property of the material that determines how well the material expands when its temperature increases. So let me see. So it's a property of the material. And the higher or the bigger the coefficient of linear expansion is, the faster and the more the material expands. The faster and the more the material. Okay. Right, and so different materials have different coefficients of linear expansion, and therefore different materials expand at different rates. For the volume of the material, it takes on a similar form. So the change in volume of a material will also be proportional to the change in temperature, meaning the bigger the change in temperature is, the bigger the change in volume is. V0 is, of course, the original volume. And we also see here a constant, which is called beta. So we read this Greek symbol as beta, which is called the coefficient of volume expansion, which is also the property of the material, meaning the bigger the coefficient of expansion is, the faster and the more the volume of the object increases or expands. Okay. So yeah, so these two equations relate the expansion of the length, delta L, and the expansion of the volume, delta V, when the temperature increases by a factor of delta T for both cases, right? So alpha and beta, they are coefficients of expansion. And as I've mentioned, it's a property of the material. Okay, so let's look at an example of how we use those equations. So an experimental organic compound is heated from 30 degrees Celsius to 212 degrees Celsius. So there's an increase in temperature there. Initially, the volume of the compound is 1 times 10 to the minus 4 cubic meters. We know that when the temperature of that compound increases, that compound will expand. And so we want to determine what will be the new volume of the compound after heating, after it had expanded. And the coefficient of volume expansion for the compound is given here. So it's a volume expansion, meaning this is beta. Beta, coefficient of volume expansion. So you have here the initial temperature, so 30 degrees Celsius. So let's just write down what's given. 30 degrees Celsius, that's the initial temperature. Right, and then it increases to 212 degrees Celsius, so that's the final temperature T sub F. Okay, the initial volume, V initial 1 times 10 to the minus 4 cubic meters, and then of course beta is equal to 2.2 times 10 to the minus 4 per Kelvin. And we want to find the final volume. Okay, so first let's look at the units. So the volume should be in cubic meters. So that's already in cubic meters for the initial volume. Then automatically the final volume will be in cubic meters as well. So notice the initial temperature and final temperatures, they're both in degrees Celsius. The coefficient of volume expansion is in inverse Kelvin. So your units have to be consistent. Okay, so there are two approaches to the units here. You can either convert this 30 degrees Celsius to Kelvin. So you can go add 273 to the degrees Celsius temperatures. I'm just getting my calculator. So say 273, 30 plus 273, you have 303 Kelvin, or you can do 212 plus 273, 485 Kelvin. Okay. So you can do that. You can convert your temperatures to Kelvin so that all your temperatures are have the same unit. Alternatively, if you for example, you forgot to convert your temperatures to Kelvin, notice how the equation, the change in volume is equal to the coefficient of volume expansion times the original volume. I'll use VI just to be consistent because that's what we used. Times the change in temperature. Okay. So yeah, so in the equation for the change in volume, we can see here that it's a change in temperature. And we learned earlier that if you're getting the change in temperature, degrees Celsius is equal to degrees Kelvin. So if you forgot to say convert your temperatures to Kelvin, then that should also be all right. So if you get the change in temperature for in Kelvin, you'll have 182 Kelvin. For the change in temperature, just subtracting 485 minus 303, you'll have 182 Kelvin. Or if you also did the change in temperature 212 minus 30 degrees Celsius, you'll also see that that will be 182 degrees Celsius. Okay, so you can see there that regardless of whether you've converted 30 degrees Celsius and 212 degrees Celsius into Kelvin or not, the change in temperature will still be 182. Okay. Right. Does that make sense? Are we happy with that? Yep. Cool. All right. So we've written down everything we know, and then we have our equation here. So change in temperature, it's 182 Kelvin. So we'll use the Kelvin one because our coefficient of volume expansion is in inverse Kelvin. So change in temperature is 182. The initial volume, we know that it's given, and the coefficient of volume expansion is also given. So therefore, we can solve for our change in volume which is the coefficient of volume expansion 2.2 times 10 to the minus 4 times the initial volume 1 times 10 to the minus 4 times the change in temperature, which we've sorted out to be 182. So your change in volume will be 4.004 times 10 to the minus 6 meter cube. Right, so I won't round at this stage because what we want to find is actually the actual final volume instead of the change in volume. So what we can get from the equation is the change in volume delta V, but what we want in the end is the final volume VF. And we know that change in volume is equal to final volume minus initial volume. So therefore, the final volume will be the initial volume plus whatever change in volume that you've calculated, right? Okay, yeah, intuitively, you also know that the volume increased, so therefore the final volume will be the initial volume plus whatever the increase in the volume is. So the initial volume was 1 times 10 to the minus 4 cubic meters plus the change in volume that you've found, 4.004 times 10 to the minus 6 cubic meters. That will be a final volume of 1.04 times 10 to the minus 4 cubic meters. Right. All right, are we happy with the solution for the final volume, or are there questions? Okay, good. All right, I see thumbs up there, so I think we're okay. Yeah, so now let's talk about water. So as Oksana asked earlier, so notice in this video, a bottle of water, so initially it was liquid. And yep, so liquid water, and then it was frozen. So notice how, yeah, what will happen in this time-lapse video, the water is now starting to freeze. Right, it's like watching water boil. It'll take forever. So just keep watching the green bottle there. You'll see how the ice is starting to form as water is starting to freeze. Yeah, and then eventually the bottle broke. Okay. And you can see there, it means that the ice expanded dramatically in order to cause the bottle to break. Yeah, so you can see there the expansion of ice when it freezes, and that's quite unusual because we said that objects should contract when the temperature should decrease, except for water. So here is the graph of the volume of water as a function of temperature. So the y-axis is volume, x-axis is temperature. So if we start from a high temperature, then we see the usual case, right? So as the temperature decreases, notice how the volume of the water also decreases as the water contracts, and that's usual. But as it approaches the freezing point, so 0 degrees is the freezing point of water. As it approaches the freezing point and as liquid water turns into ice, notice this big jump in the volume Right, so suddenly the volume of ice increases before it again starts to decrease as the temperature continues to decrease. So there's this unusual behavior around the freezing point 0 degrees Celsius. And so if we expand this point and look at this figure here, so this is just the expanded part around the freezing point from 0 degrees Celsius to around 18 degrees Celsius. We'll see here the usual contraction of water as the temperature decreases. Okay, but it sort of contracts only about until about 4 degrees Celsius. So 4 degrees Celsius is sort of a special temperature, and then about at the temperature lower than 4 degrees Celsius, notice how the volume of the water starts to expand. Okay, so around 4 degrees Celsius is where the unusual behavior of water starts. And we can sort of explain that by looking at the ice crystals that are being formed as water freezes into ice. So below 4 degrees Celsius, water starts to freeze, and so ice crystals start to form. And the ice crystals have a bigger volume compared to the water molecules. So you can see here that the ice crystals sort of are bloated. So they have a bigger volume. Okay? Bigger volume for the ice crystals means that overall the water will expand. Okay? Yeah, the water will expand as it approaches its freezing point 0 degrees Celsius. Before the ice crystals form, you have their smaller ice crystals being formed, and so you have smaller volumes. That means that you have a contraction in the ice crystals as you try to. So we'll just do the reverse now. So from the ice crystals that are bloated and have bigger volume, if you try to heat up these ice crystals, the ice crystals will collapse, okay, as they lose their shape and turn into liquid water. So you have there a smaller volume, and at 4 degrees Celsius is again the point where the ice crystals start to contract. Okay. And so above 4 degrees Celsius, you have this usual expansion as the water molecules now start to move faster and expand the water above 4 degrees Celsius. Okay. Right. So 4 degrees Celsius is just the special temperature where our ice crystals start to form, and ice crystals bloat the water as it turns into ice, and that's why the water starts to expand when you have ice there. If we look at the density, right, expanding, so density was defined as mass over volume. So there's an inverse proportionality between density and volume, meaning as the volume increases, the density decreases, right? So that's the inverse proportionality relationship. If one increases, the other decreases. In this case, when volume increases, the density decreases. So for the ice crystals below 4 degrees Celsius, so that's the first here, number 1, below 4 degrees Celsius, when you have a lot of bloated ice crystals with very large volumes, high volume means low density, and so the ice crystals will have less density. And that's also the reason why ice floats to the surface of the water, because ice is less dense than liquid water, and less dense floats above more dense liquids, right? Okay, at 4 degrees Celsius, when the water contracts, it will have small volume. So small volume means high density. So at 4 degrees Celsius, it will be more dense. It will actually achieve its maximum density at 4 degrees Celsius when the ice crystals are starting to collapse. Okay. And above 4 degrees Celsius, okay, the water, liquid water, now starts to expand as you increase the temperature because the water molecules start to vibrate faster, causing the water to expand. And so the expanding water means higher volume, and higher volume means smaller density. So the expanding water above 4 degrees Celsius will also have less density. Okay. Right. So it's this peculiar behavior of water which causes, that helps water life to survive in cold, freezing temperatures. So if you think about a frozen lake, do you think a frozen lake will freeze all throughout from the surface to the bottom? It's probably unlikely. Yeah, it's unlikely for a lake to freeze over all throughout because of water's unusual behavior. So at 4 degrees Celsius, water is the most dense water. So that 4 degrees Celsius water will always sink to the bottom of the lake, even if the surface is frozen. Okay. It's unlikely for the bottom to freeze, and that's why, you know, even in Alaska, they're able to fish under, you know, a frozen lake because you have this liquid water that's supporting life underwater. So if you look at the temperature of a frozen lake, you have their very cold temperature, and you have ice, which is at freezing point 0 degrees Celsius. But then you have the most dense water always sinks down to the bottom of the lake. Okay. Yeah, and yeah, so that actually ends our lecture on temperature. We've seen that temperature should be measured in Kelvin, being the SI or basic units, but in common thermometers measure temperature in degrees Celsius, so we should know how to convert Celsius to Kelvin. And we learned that as the temperature increases, the objects expand, except for water at 4 degrees Celsius. And we can quantify the expansion in the length and expansion in the volume of the objects via these two equations. All right. Okay, so so that ends the lecture, and we have the workshop following that, where we can practice the concepts that we've learned. But I'll give you time to look at the workshop questions. Maybe let's see how much time we need. So the first part is converting temperature from Celsius to Kelvin and vice versa. Second question is about water's unusual behavior. And then the third question is about the expansion of materials applied to a physiological problem. So maybe let's just meet again at 10:30. Do you think 20 minutes is enough for you to have a look at the questions? Yeah. Okay, so I'll give you until 10:30 to have a go at the workshop questions, and then at 10:30, we'll meet again to discuss the solutions. I won't end the Zoom call, so you can stay there. I'll just mute my microphone. But if you have any questions, feel free to pop them into the chat box, and I'll be able to read them and respond to them. I'll